All right. Hi, everyone. In this video, I'm going to go over the solutions, just add a little bit more explanation to the Kinematic Quiz review solutions so that if you had any questions, hopefully the video would answer it. So I'm looking at this first graph. This is a position versus time graph. We note that it starts out very steep and it ends up very flat. So that tells us that it's moving very quickly at the beginning because the slope is really steep, and that at the end, it is going really slowly. It's basically flat right there, meaning it's basically stopped. So that's where I got this written description of the object starts at 0 meters because it starts here at 0, moving quickly in the positive direction because it's very steep, and it slows coming to rest after 10 seconds because it is flat after 10 seconds. I think number two is pretty straightforward. The object is going faster at 2 seconds than at 6 seconds because the slope is steeper at 2 seconds than 6 seconds. I think that's pretty self-explanatory, right? The slope of this graph is the velocity, so the steeper the slope, the faster it's going. So, in number two, it's first asked compare the displacement. So the displacement is how far you are from where you started. So they both end at 2 seconds, and they both start um, they both end at 5 meters, and they both start at 25 meters. So right, as we take a look at A starts out really slowly and then gets faster and faster and faster, meaning because it's getting steeper and steeper, versus B has a constant slope, meaning it has just a constant velocity the entire time. So um, the displacement is the same because they both start and end at the same location. So displacement is just your final position minus your initial position, and they both start at 25 and end at 5. So they both travel 20 meters basically. Right. Also, this one's now, once you know the equation for the average velocity, which is just the displacement divided by the time, since the displacement is the same 20 meters and the time is the same 2 seconds, they would have the same average velocity, which is 10 meters per second. And looking at these ones, right, we have a negative constant slope, so that's a negative constant velocity, and then a slope of 0, so a slope, the velocity is 0. For the acceleration, right, the slopes of both of these lines are 0, so the acceleration is 0 the entire time. On this one, it starts out very steep positive and then flattens out by the time you get to the middle. That tells us that we start out very quickly, and by the time we reach the middle, we should be stopped. And then, right, it starts to get steeper, but in the negative direction, right? Steeper, but in the negative direction, meaning we're speeding up in the negative direction. This could be like a ball that is pushed up a ramp, so it's traveling, towards the top of the ramp and then stopped at the top and then rolling back down towards the bottom. That kind of motion would create a graph that looks like this. Also, if we were to just throw a ball straight up in the air and let it come back down, it would also create a motion like this. The slope of this velocity versus time graph in here is negative and constant, so hence the negative and constant acceleration. Looking at this one, right, it starts out flat, so the velocity starts out 0, and then it speeds up, gets right by because it gets steeper and steeper and steeper. So that tells me that my velocity increases, and then the slope stays constant from right before the dotted line to right after the dotted line, then holds that same slope the entire time, turns into a linear line. So therefore, the slope, since the slope becomes constant, so right, the velocity becomes constant. Looking at to make the acceleration graph, you have a constant positive slope right here. That's going to tell you a constant positive acceleration. And then the slope after the dotted line is 0. So therefore, the acceleration is 0. We have a tailback initially running at a velocity of 5 meters per second. So that's going to be V naught. Becomes very tired and slows down at a uniform rate of negative or 0.25 meters per second squared. How fast will he be running after he goes an additional 10 meters? So this needs to be negative because we're traveling in the positive direction, but we're slowing down. So you got to put a negative sign on that 0.25, that acceleration. Looking at everything you have, right, we don't have time. That's pretty notable. We have initial velocity. We're looking for the final velocity, and we have 10 meters. So it tells you you're going to want the Ringo equation. You're solving for V. You have your initial velocity. You have your acceleration, and you got your delta, the distance they traveled, the displacement there. So A ball is thrown straight down on the bridge with a constant initial velocity of 18.5 meters per second. If it travels for 2.3 seconds, how high is the bridge? So because it only ever travels downward, never upward, it would make sense to make down the positive direction. So that's meaning you're going to make the 18.5 and the 9.8 are both positive because they're both downward, right? The 18.5 is your initial velocity and it's a downward velocity. So, and the 9.8 meters per second is also a downward acceleration. So we would make both of those positive because we're choosing down to be positive. Putting an initial velocity, initial position of 0, it would make sense to make these y's instead of x's. So I apologize that there are x's in the solutions. That's not necessarily the way it should be. Um, but anyway, your initial position is 0. You want 0 to be at the top, and you're looking for x at the bottom or y at the bottom. And the reason you would do that is because you want it to, right, to get, as you go downwards, you want the positions to increase. So you want 0 to be at the top and your final position to be 0 down, get bigger as you go down because you chose down to be positive. Otherwise, you set it up that way, you should get 68.47. You can round however you want. I think once you've looked at this, read the direction or read the answer, it makes sense. But you have a velocity versus time graph here, and that velocity versus time graph is curved, right? We don't see that very often, and so that's kind of a surprise. The reason that it's curved is because so right, we see the slope of this graph is the acceleration, and so we see that the acceleration would be decreasing as time goes on. And so it says, what can be said about the acceleration of the skydiver? So the acceleration of the skydiver is decreasing because the slope of the velocity versus time graph is decreasing. This means that the speed of the skydiver increases by smaller and smaller amounts, not that the skydiver is slowing down. So, right, because sometimes people think that the skydiver is slowing down. They're not slowing down. They're reaching a constant speed of about 55 meters per second. So it just means that at some point they're going to end up going at a constant speed. All this question is really getting at is, do you know can you interpret a graph? So yes, this is a situation we haven't really seen before, but it's not asking you anything super surprising because you should know that the slope of position or velocity versus time graph is acceleration, and then we just see that the slope is getting flatter. So as we think about this real world situation, like why would that be? Well, the faster you go, the more air resistance there is. And so at some point, you're going to reach what is called um, terminal velocity. And that's basically when you're not going to go any faster. And it's because the force of gravity is canceled out by the force of air resistance. So anyway, more basically, the air resistance is going to stop you from accelerating anymore. So that's what's going on there. Lastly, we have Mark Watney from The Martian. Basically, is on Mars or is trying to figure out the acceleration due to gravity on Mars. And this bit about it should be noted that the density of atmosphere is 1.2. All that's telling you is that you can ignore air resistance. So the first thing to do is average your times. Since they're all for the same distance, you can just simply average the times. So add them all together, divide by the number of them, which is 5, and you're going to get that the average velocity time is 1.374. You could round it differently if you wanted to. That's going to go into the John equation. Again, you'd probably use y's here instead of x's, but the initial velocity is 0 because you've dropped it. And you're looking for A, you dropped it 4.3 meters, and there you go, there's your acceleration of 4.56 meters. So it turns out that the acceleration due to gravity is actually 3.7. I'll give 2 specific ways that Mark Watney could improve his experiment. This is going to be less important for the quiz that you're taking coming up, but still kind of important to think about. But he could increase the distance that he drops it. This would increase the amount of time the ball is in the air for, thus decreasing the error resulting from human inaccuracy and timing, right? So every time you try to time something, you have error when you start the stopwatch and when you stop the stopwatch. And so if you can make it fall for a longer amount of time, then that error becomes a smaller percentage of your total time. So like if let's just say your error was 0.2 seconds and it only falls for like 0.3 seconds, then right? That's a pretty big error in your time that could be a result of you not clicking it very well, versus if it falls for like, right, if your error is zero point 0.2 seconds and you let it fall for like 2 seconds, then that, right, becomes a much smaller percentage of your total time. He could rig up some more accurate timing system to help him get more accurate data, meaning maybe he's got some sort of electric thing that starts the timer right when it lets go, or something to that effect. He could also just simply take more trials, would also help increase the accuracy. So there you go. Those are the solutions. Hope that helps. Good luck.